to Rocket Money for supporting PBS. Two protons next to each other in an atomic nucleus are repelling each other electromagnetically with enough force to lift a medium-sized labradoodle off the ground. Release this energy and you have a nuclear explosion. Just as well there exists an even stronger force than electromagnetism holding our nuclei together. But it's not the strong force as you might have imagined, at least not directly. Nuclei are held together by a quirk of nature, without which we would have no complex atoms, no chemistry, and certainly no labradoodles. Quantum chromodynamics is a complicated sounding name, but the fundamental force of nature that it describes, the strong force, is actually even more complicated than it sounds. In our previous episode on this topic, we saw how the strong force binds the elementary quarks into protons and neutrons, but that's where we left it. Based on what we learned in that episode, the strong force is entirely confined to the nucleons, and yet somehow it's also the force that binds protons and neutrons together to form most atomic nuclei. That process is strange enough that it deserves its own episode.
$100 billion budget, Hamiltonian, cities, counties, broken down, QMP, London, Tokyo, or London, New York, and Tokyo time, or bedtime on London, New York, Tokyo, QMP. We'll get to these little wiggly squiggly what they're doing. The Faraday suit.
Who graduated from the University of Osaka in 1929 before moving back in with his parents and working for no money as a university assistant due to the Great Depression, not because he wasn't a great physicist.
It was like looking at a cipher code and
saw was focused on the problem of how nucleons stick together. He was perplexed
you didn't tell this guy how he pulls it off.
Shouldn't be observable outside atomic nuclei. Yukawa had one intriguing clue to the inner lives of nuclei, and that was beta decay. The tendency of large nuclei to occasionally spit out
well
an electron,
for me
and in the
stepping in
process
for the very first
one of
time
their
after
neutrons to a
watching,
proton.
looking, and like, whoa,
He knew that the electromagnetic
playing
force is
regular
communicated by
stocks
the
for the
exchange
week,
of photons,
trying to figure out
and so
this
it
thing,
stood
but
to reason
really
that this
getting
nuclear
into
force
this thing,
should be
at least this
mediated by
setup, because
some
I
particle.
started to see some
So what if this
cycles and
particle was the electron,
started to
and
work.
beta decay
And so
was the side
when you're
effect
here,
of the exchange of electrons
we'll get
between
into that.
nucleons. Like if protons and
find a
neutrons
tighter
were playing catch with the electron, and sometimes they fumbled the ball.
These are the good
It turns out
science,
this
right?
is totally not what's happening.
You know,
But the insight that
when do
forces should be
you
mediated by a particle
get
was
those
new in its
on
time,
what
and it eventually led
cycle
Yukawa
size
to the right answer.
to what's
Having an
coming in?
exchange particle with mass,
You would
unlike the
almost want
massless
it to.
photon,
And things
is a
about,
great
you know,
first
like,
step
okay,
for making
do
a
this. I was like,
short-range
really? I was
force.
like, well,
These
chugga, chugga, chugga,
exchange
chugga,
particles
chugga,
are what we
and
call
I might have
virtual
a
particles,
big
which
one
we've discussed
here,
before.
because
Virtual particles
glad I did.
sort of break the laws of physics in the sense that they can pluck the energy needed for their existence out of nowhere, as long as they give it back again. This is a result of the Heisenberg uncertainty principle, which in one form says that we can never know both the energy and the duration of a phenomenon to better than a certain tiny accuracy. That means, for very short periods of time, the amount of energy in a patch of space can vary. Mass is a form of energy, so a virtual particle can briefly gain mass from nothing. The more mass it has, the less time it can exist. Yukawa used the electron mass to calculate the strength and range of a force that could be mediated by the electron, assuming that it was traveling at near the speed of light. The resulting force turned out to be around only 1/200th of the strength needed to hold the nucleus together, and had a range much larger than the size of the atomic nucleus, so the electron couldn't really be the particle mediating this nuclear force. But Yukawa now had an equation that described the type of force he wanted. He adjusted the equation to describe a force with the appropriate strength and range, and found that it required a much more massive exchange particle. He called this hypothetical particle the meson, from the Greek mesos for middle, because it had to have a mass somewhere between the masses of the proton and the electron. Yukawa also predicted that these particles had to have electric charge. Just like with beta decay, a neutron could emit a negative meson and transform to a proton, or a proton could emit a positive meson and transform to a neutron, and the neutral meson could be exchanged between protons or between neutrons. As a result, Yukawa predicted 3 meson types, one for each possible charge value. Unfortunately, this new theory didn't explain beta decay at all. In fact, Yukawa reasoned that beta decay required a completely different nuclear force, much weaker than the one holding the nucleus together. In fact, he correctly predicted the existence of both the strong and the weak forces at the same time, although the weak force isn't really mediated by electrons, and we have videos explaining everything you probably want to know about it. Yukawa published his theory in 1935, and it was almost completely ignored. To be
Way
fair,
nicer that way
first, the
than
existence of 2 new forces of nature was an
somebody not having to
extraordinary
stop
claim,
off, stop
and
right.
such claims require extraordinary evidence. No one was going to believe this until we detected
Back to
a
those little
meson.
triangle
These
games,
days, we
or
routinely
rectangle games,
create
triangle
countless
games.
mesons by smashing atoms together in our particle accelerators. But back then, particle accelerators were just being developed, so we had to rely on cosmic rays. These are high-energy particles that rain down on the Earth from natural space particle accelerators.
There is no
like
way
supernovae
Free
and
Solo.
quasars.
No way.
Yukawa wrote a letter to Nature magazine explaining why cosmic radiation could contain mesons, hoping to inspire other researchers to look for these, but his letter was rejected. Nonetheless, others had independently thought of searching for new particles in cosmic radiation. We have Vibha Chaudhry and Devendra Mohan Bose, for example, who developed a method using photographic plates. They set these up at high altitudes in India and Tibet due to the fact that our atmosphere
Creeping
is so
in
good
there.
at blocking cosmic rays,
First
which
time
is
Higgs
annoying
yelled
if you're
at
a
me, the
particle
second
physicist,
time,
but great
the
if
second
you're
time,
anyone else.
clipped me,
Chaudhry and
you know,
Bose
soft
even
bottom
spotted
on
the meson at
on
around
what
the
that
mass
is,
Yukawa
started
predicted.
rolling, not really
Sadly,
paying
the research
attention.
went mostly
The
unnoticed
super high
until
spike,
British
but
scientists
only pegged in
independently
here.
found mesons in 1947.
It come down,
Anyway,
figured,
not only were these
right,
new
you know,
particles
like
at the
good,
right
she's
mass
starting to
range,
roll down,
there
maybe
were
she
3
won't.
of them,
She
just as
didn't like
predicted
it,
by
kinda
Yukawa,
just,
one positive, one negative, and one neutrally charged. But then things got kinda awkward. Over the next couple of years, thanks to better particle accelerators
yes,
and
better that
improved
way.
understanding
2/3
of
the time you
radiation,
want, alright,
more
well,
and more mesons were
shame on
discovered
me.
with a range of properties. The first mesons, the ones found by Bose and Chaudhry, are called pions, and these are the particles actually exchanged by protons and neutrons in the nucleus. There are many others.
Like, yeah.
Kaons, eta
Yeah,
mesons,
look at that.
B
She
mesons, B
was
mesons,
running
etc.
hot down
And to
there.
make
This
matters worse,
popped up.
scientists also found more
She
particles
didn't
that
bust
could
over.
exchange
Right,
mesons,
nothing
just
wrong
like
with that.
protons and
There's
neutrons would.
nothing wrong.
These particles were named baryons, after the Greek word for heavy. There was the lambda, the sigma, the xi, the omega, and more. Again, all with different masses, charges, and spins. This endless collection of baryons and mesons came to be known as the particle zoo, and it was a huge problem for physics at the time. According to Yukawa's theory, the atomic nucleus only needs 2 baryons, the proton and the neutron, and 3 mesons, the pions. So what was with all of this extra junk that nature doesn't seem to use outside of particle accelerators? This problem was finally solved by Murray Gell-Mann, who realized that mesons and baryons are not elementary particles, but rather made up of quarks. Hadron is the general name for a particle made of multiple quarks. The particle zoo just results from all the quark combinations that are possible. We covered this in our episode on quantum chromodynamics, but here's a quick refresher so we can get to the punchline of this video. With the discovery of quarks, it was clear that we needed the strong force to not only hold the nucleus together, but also hold nucleons together. In fact, the latter is what the strong force really does. Binding nucleons is sort of an afterthought and not quite directly what the strong force does. So, just as electromagnetism works on things with electric charge, the strong force works on things with color charge. There are 3 types of color charge, unlike the single type of electric charge. A quark, for example, could have a color charge of red or green or blue, or the opposite color charges of anti-red, anti-green, or anti-blue. These names, by the way, are just analogies. composite particles need to be color neutral. So the three quark baryons have one of each color charge, which cancel each other out.
I saw
while
it.
two
We all
quarks
saw
of
it.
the meson
You know which one
have
it
a
was.
color
We
and
get
its
it.
anti-color. These quarks are bound by the strong force, which is mediated by a
That
massless
one,
particle
maybe?
called
This one.
gluon.
Yeah, it was this one.
Gluons
I was
each
like,
carry one regular and one anti-color charge, and they cause the colors of quarks to flip when absorbed. Baryons and mesons are held together by a continuous exchange of virtual gluons. But wait a minute, haven't we been saying the entire time that the reason the strong force has a short range is because it's transmitted by mesons with mass? Well, that was Yukawa's whole deal, but now it turns out that mesons aren't the real exchange particles of the strong force, and the real ones, the gluons, don't have mass? What's going on? Actually, the color-neutral hadrons can't even feel the strong force directly, just as electrically neutral objects don't exert an electrostatic force on each other. But there is a workaround. Atoms seem electrically neutral from afar, but if you are close enough to the nucleus, you would feel its positive electric charge. Similarly, if protons or neutrons get close enough to each other, their internal quarks will feel each other's presence. A quark from, say, a proton will want to tug at a quark from a neighboring neutron, but they can't simply exchange a gluon to do that, because gluons have color charge, so exchanging a gluon would cause the hadrons to no longer be color neutral, which is not allowed. In order to properly feel the strong force, the hadrons need to exchange a neutral particle, and nature has found a way to make that happen. Here's how it goes. A pair of nucleons get close, and a quark from one gets pulled towards the other. Its gluon connection to the other quarks in its nucleus, what we call a flux tube, extends and snaps, and in the process generates two new quarks. One remains in the nucleus, while the other forms a quark-antiquark pair with the original escaped quark. This is our meson, our pion. It's color neutral, so it can be absorbed by the second nucleus without breaking any physics. There, one of the meson's quarks annihilates with an antiquark counterpart in that nucleus. Ultimately, we're left with two nucleons of the same type that we started with, but they've now communicated the strong force. They did it in a roundabout way, but the process nonetheless exchanged energy and momentum, binding the particles together. This is how the strong force finds its way around its lack of a neutral gluon. It cobbles together a neutral exchange particle, the meson. But the meson has mass. A virtual meson has to borrow a lot of energy to create its own mass, and so the uncertainty principle says that it can't exist for very long. Its range defines the possible size of an atomic nucleus. If a nucleus gets too big, then its nucleons are too far apart to exchange mesons effectively, and it'll decay. By the way, when we talk about the force between quarks, we call it the strong force, but this residual strong force that exists between nucleons is called the strong nuclear force. You know, this reminds me of our episode about quasiparticles. In that episode, we talked about how fields can arise as emergent behaviors of other fields, and these quasi-fields will have their own quasi-forces and quasi-particles. Well, that's sort of what's happening here. The strong nuclear force is a quasi-force mediated by a quasi-particle, the meson. Without this little quirk of nature, this emergence of a force that's not really supposed to be there, the most complex atom in the universe would be hydrogen. Fortunately, nature stumbled on a way to bind the nuclei, which gave us chemistry and biology and ourselves, including a young physicist named Hideki Yukawa, who was able to figure out some of the most important forces from which emerges this richly complex space-time. Thank you to Rocket Money for supporting PBS.